we'll go for like, 45 minutes here, half hour, 45. We'll see how long I get through this lecture, and then we'll have lunch. So this lecture is number 8, and lecture number 8 is on object-oriented databases and object-oriented techniques and features of Oracle. So looking at advanced database applications, usability of the relational database model for advanced database applications, object-oriented concepts, and then the problems of storing objects in relational databases, and then the next generation of database systems. So this one here is looking at and focusing on applications for databases that are in the area of computer-aided design, computer-aided manufacturing, case tools for software engineering, and office information systems. I think this is probably the biggest area, the office information systems. Digital publishing, this is also a big area for database development these days and new trends. Digital publishing meaning making videos and movies and multimedia available and using database technology to store it. It's very, very efficient to put it all together, very inefficient using a relational database model, especially when you got to query a table and then take a 2 gig file out of it or 3 gig file out of it. Or even a 1 gig file out of a database table. That's just too big. So it can actually make your database unusable to a certain point if you have too many large binary objects inside of it or too many large objects in general. So looking at the interactive and dynamic websites and pages that are associated with databases, and then other applications for complex unrelated objects and procedural data. In terms of computer-aided design, how is that going to be facilitated using database technology? We're looking at storing the data that's related to the mechanical or the electrical designs or, computer-aided designs, architectural designs, buildings, airplanes, integrated circuit chips, board designs. They're time-consuming, they're huge, they're big. You can actually use a database application integrated with your CAD system or CAD systems that use database technology actually, to keep track of a repository of all the parts and pieces and all the information needed. If you're doing that, then you can query it for reports, for parts lists, even for common parts, specs, and all sorts of different things that can come out of that. So the design of this type has common characteristics to it. The data has many different types. So the data could be a picture, it could be an audio file, it could be a description of a type, in terms of text. Can we keep the volume down in the back? So the group that sits over here is now sitting over there today. I'll just wait for them. Thank you. Yes, I was waiting for you to finish so I could talk next. Thank you. All right, so the data has many different types associated with it with a small number of instances. So the designs may be very large as well, which causes some interesting design challenges. And the person who was talking was our TA, I believe, as well. That's a really good example. All right, so the design is not static. It evolves through time, which is an interesting phenomenon. So the updates are far-fetched, far-reaching. Involves version changes, configuration management, cooperative engineering. So the nature of the application really does sort of lend itself well to a database concept, but the design of the database needs to take into those characteristics into consideration so it can be efficient in terms of its feature options. So we also have computer-aided manufacturing, very similar to computer-aided design, stores similar data, plus more data about discrete production, which means we're going to have production schedules and things that we can add in there that we could link to the design. So we could actually take the sub-assemblies out of the design, create production schedules, put that into or integrated in with a production line setup with maybe a staffing scheduling system, and then we can do our whole manufacturing and put it through a same database and then query different combinations and come up with the optimal design configuration. So computer-aided software engineering also works on the same concept, stores data about the stages of the development life cycle using requirements, an analysis, a design, and implementation phase, and then having different sections of the database supporting that and those features. Believe it or not, network management systems can also be utilized in a database, and if you did one of the assignments, well, you had an option to skip one, so you may not have done this assignment, but if you did the assignment, They said to compare a hierarchical with a networked, with a file, with an object-oriented, with a relational database. This is some of the information you could have used for it, or maybe you're still writing it. So here's some of the information you could have used for it. A network actually is a database structure in itself. There is a such thing as a networked database. In a network management system, we're coordinating the delivery of communication services across the network. We're performing tasks on the network path. We're handling complex data. We're coming up with routines and connections and diagnosing problems and things. We could represent that in the form of a database structure as well. We could also represent, and this is what I was going to say, the most commonly used form of the database these days is for office information systems and office automation for the most part, and multimedia systems. So storing data related to computer controls in the business itself, electronic mail, documents, invoices, and so on. Documents also structured in XML, HTML, different formats. You can actually use this as a document retrieval system in terms of a database application to be set up for that. Digital publishing, another area of common use for database technology, becoming possible to store books, journals, papers. Well, that's sort of like iTunes, actually. A huge database, lots of stuff in it, books, movies, music files, that are stored in a database structure that, each user who downloads a copy of a particular book is getting the same download, same copy, same digital asset, which makes for consistency, digital rights management, all sorts of different unique features that can be built into the database management system. And the amount of information that we put online, we make available is huge. So making the largest database ever has to be managed and manageable. So we have to be able to manage the database. So we have to be able to make sure that we can put large amounts of data inside of a system. And most people use the graphical information systems on a daily basis if you use a GPS, and that's coming from a database application again. So you might start to get the picture that databases are used for practically everything these days. You can't use a relational database model for geographical information systems either, by the way. It's just too big. In fact, all of the examples I'm giving you don't lend themselves well to a relational database model because it makes, well, for various different reasons I'm going to go through next, but it makes it difficult. You can't query a database that has that much data in it. It's too big. And also, for the most part, the structure isn't lending itself well. Why do we want to query for that? Why don't we just connect the objects and have the objects tell us what's there? So an object-oriented approach to it makes a lot more sense. Going back to the geographical information system, it's the spatial information, the terrain, the things about the area. Much of the data is derived from surveys, satellite maps, photographs, and things. It has a tendency to be big. Lots of shapes, lots of colors, lots of patterns. We may not necessarily know even how to identify that into columns, as an example. Databases are also used for interactive and dynamic websites to save preferences about something, to save things in terms of components that the user has purchased, something of that nature. So consider a website for online catalog for selling clothes. Website maintains a set of preferences for the visitors. So you can obtain a 3D rendering of the item itself as well. Maybe the color, the size, the fabric. Modify the rendering by the account so you can rotate things around and stuff. Select accessories maybe that go with an outfit. So you need to handle multimedia components, pictures that go along with the descriptions of items and things, and interactivity and based on these preferences and on the selections that were made. So that's also very labor intensive because you still have to go, pull a picture out of a relational database model and then stick the picture onto the website. Very slow, and then make this picture work with another object to make it interactive, to make it resizable or to make it rotate or something. And then again in fact you'll probably notice a lot of shopping cart applications, if they even show you a picture, you're lucky. They're not going to show you a picture of the item. You've already seen the item. You just get the textual description down there. Why is that? Because you can't, it's too labor intensive to bring the picture out when you're doing the shopping cart because you have multiple pictures. It's not cached, it's per the item that you selected. That whole application is going to run too slow. so you don't want to make it run that slow. Instead, you're going to pull out just the text part of it. So let me go through some weaknesses of the relational database management system and the relational model in general. Poor representation of the real-world entities. So now that we've done entity relationship diagrams and we've translated those diagrams into tables and we represented them with columns for the attributes and we did all that stuff, then we figure out, well, it's a bad representation for the real world. In essence, it actually is when you compare it with object orientation, because object orientation takes into consideration roles and associations and information that entity relationships don't take into consideration. Also, normalization leads to relations that do not represent or correspond to entities in the real world. So we took and we went through normalization last time and we created tables that didn't exist out of the entity relationship diagram. So we made up stuff to make it normalized so that we could fit these rules in terms of normalization. So the more we normalize the data, the less real it is, the less we're actually representing the real world. So there is a big pull towards object-oriented databases because it represents a more true version of the real world. Also, the semantics of overloading don't exist in relational database model. So relational model has only one construct for representing the data and the data relationships, which is the relation. How are you going to overload a key? You can't overload a key. How are you going to change a key? You can't. How are you going to make a key polymorphic? You can't make a key polymorphic. A key is a key. A student ID is a student ID. Well, what if you've got multiple students with different IDs? That would have been an overloaded concept in an object-oriented database. Not possible. In a relational database model, there's an entire concept of overloading, which is actually needed with real-world objects. It doesn't exist. There's no capability. So the relational model is semantically overloaded. It is actually, more ways than one. But it isn't overloaded in the true sense of object orientation. So you're only looking at the relationship. The relationship is semantically overloaded because one student takes classes. Well, that's graduate students taking classes, undergraduate students taking classes, maybe online students taking classes, foreign students taking classes, domestic. That's semantically overloaded. We're not really specifying who's taking a class. So we take that model and we represented all students. Then according to the model, we could have violated our rules a little bit because we could say, well, then international students can take online classes. Well, they can, just one. How are you going to put that rule into the database? That's a tough one too. When all students can take classes. So as a relational database model, it doesn't work well for business scenarios with different types of relationships to actually support the concept of overloaded objects. Support, poor support for integrity and enterprise constraints. Yep, we have data constraints that are well represented in the form of key constraints. But what about integrity for enterprise constraints? So I'm actually going back to that concept of, yes, we can put a key in, so one student enrolls in one course, but they've already taken an online course. So in order to fix that problem, there is support for it. We make another table, and the other table we make is online registrations. And in there we have student, course, student, course, student, course. So if you're in the table of the online registrations, then you can't be in there more than once. Then we can enforce that as a business rule or as an enterprise constraint. We can say that at I2, international students can only take one online class. Therefore, if they're in the database already, they can't get in there again. But we had to create a separate table for that to enforce a rule. So we're fixing the problem by creating more data, and then we go back to this problem up here of normalization, where we're making a real-world entity out of a non-real-world entity. We wouldn't need that table unless we were trying to figure out who's taking classes and who hasn't. So, homogeneous data structure. So relational model assumes both a horizontal and a vertical homogeneity. Well, that we've got some consistency among the data representation. So many relational database models now allow this thing called a large binary object, blog. Most people go, well, what in the world's a blog? Well, even if you know what a blog is, you don't know what's in there. So it's a large binary object. Well, could it be a large video? Could it be a video that's black and white, a video that's color, a video with audio, no audio? Maybe it's no video, maybe it's just audio. Maybe it's just a huge file that is an executable file. Maybe it's a Microsoft Word file or a PowerPoint file. We don't know, it's just large. Well, what if we could have different types of files in our object-oriented database? So it would be more of what they call the heterogeneity, where we'd have the video file is stored or used by the player, and the audio file is stored and used by the player. And then the player has multiple different types of relationships with all these different file types that can be used, instead of grouping them all together as one object and calling it a large binary object. Which is another weakness. Here's another weakness. So if you're looking for ideas to talk about in the object-oriented versus relational database model, I'm giving you the information right now. And again, this is lecture number 8 from the lecture notes. If you haven't done that assignment yet, this is where you're going to get some information that you might want to use. Another weakness. So, and all of the weaknesses for relational database management systems are strong points for object-oriented database management systems, by the way. Limited operations. So the relational model only has fixed sets of operations which cannot be extended. That is true. There are no behaviors. There's only one behavior. So, well, there's multiple actually. You can select it, you can update it, you can delete it. But you have a fixed number of operations that you can perform on the data that's in there. You can't really send it. Well, you can send it. You can send it when you query it with a join. You can send it from one point or another. You can't extend the behavior, though. You're limited to the SQL language, and you're using the SQL language to perform the behaviors on those objects, well, on that data. There's also difficulty handling recursive queries. Actually, when I went through all of the query information, did I cover recursive queries? No. Is there such thing as a recursive query? No. You can possibly put together one in PLSQL or using JDBC by creating a Java loop that runs recursively, or a method call that a recursive method call that ran a query recursively, but the query itself isn't going to run recursively. You're going to have to create some other language construct to create the recursive behavior. Extreme difficulty in producing recursive queries to non-existent. Extension proposed to the relational algebra to handle this type of query, and well, it's a unary transitive recursive closure or operation. Well, aren't we saying when we normalize that we don't want these transitive relationships? We don't want recursive relationships. We take the recursion out of the relationships when we do normalization, actually. That's the first thing we do, is we pull out all of the recursive relationships. So how are we going to query on it? But you can do that in an object-oriented environment. The object can have a relationship with itself. So it could be a staff person and a branch manager all at the same time. If you do that in a relational model, then you have two. You have a branch manager and a staff person. You have to have two separate relationships for it, or two separate objects, relations, because one of them can't be itself. So here's a recursive query, staff number with manager staff number. Well, it's basically one guy, eventually one guy is going to be managing himself. If you're the branch manager and you're a staff member who works at the branch, you're managing yourself. So this is basically the same concept. We have a bunch of staff numbers, and the staff numbers are managing. Well, this is the guy, the manager. This is the staff number, and this is the manager. So that's how we're representing it. So in a relational model. So it's a recursive query if we're running through and getting all the different combinations that could exist. So. Well, what about mismatches? So most DMLs The database manipulation languages lack computational completeness. To overcome this, SQL can be embedded in a high-level third-generation language. Because what about the mismatches? What about, well, we have wildcards, but what about the lower versus the upper? What about all of the other things we have maybe in the data and in terms of the data storage that aren't going to match up correctly? So what we do is we take, and for example, a query, we run the query, we get all the data. In fact, that's like why a lot of people just go select star from this table. And then we take the data and we copy it over into variables and we test the variables for something. And we go, oh, it's this, oh, it's that, it's less than 5, it's greater than 5. Oh, this person's a senior. And then from a programming perspective, and this is what a high-level third-generation language, you know, doesn't necessarily be, that's a high-level language. We don't have to, we can do it with C or C++ or Java, which is the third-generation language. We can test the values. We can see if there's a match between this student and this student over here, which we're not going to be able to tell from a regular old query. So the query has limitations in terms of the analysis that you can do on it. So that's why we use programming languages with it. So we might have a mismatch mixing different programming paradigms as well. Estimate that much of 30% of the programming effort in the code space is extended on types of this type of conversion. So making something equivalent, making something match, getting rid of mismatches and stuff. Turning a student into a student, an object that we can use, or a student representation of a student. Making sure that this student is a graduate student, or this student is an undergraduate student, or this, existence actually completes correctly. So it's hard to get it. It's hard to get it. Not impossible. You can build the logic in, but it's very hard to get it out of manipulation language. So they're very hard to get an equivalence. Easier to get it using a programming language. Other problems with the relational model: transactions are generally short-lived, and concurrency control protocols are not suited for long-lived transactions. One query generally works just fine, and then we commit it or we roll it back. But what about the next day, and the next day after that, and the next day after that? That's longer-lived applications. Can't control the object states. Once it's object, there's no objects. So once the query is run, then once the query is committed, the query is committed. You go on and you do another query. So it's very hard to have really long-lived transactions, because then you can't commit anything unless all the transaction, which is the approach, unless all the transactions been completed. So you take JDBC as an example, and you use that with JTA, Java Transaction Authority, and you make long-lived. Well, you're using it in a programming language. We're talking about Java. Then you make long-lived transactions that can be supported through the relational model. But you're using the transaction authority and the management of those transaction objects to actually facilitate this behavior. You can't do it from a database. Once you commit, you commit. Once you roll back, you roll back. Once you do a transaction of some sort, once you've defined the transaction, the shorter it is, the easier it is. Outside, you've opened up a connection and you've locked a bunch of tables. You're going to leave that out for 5 days? Not going to be very efficient. Are you going to leave it out for 1 day? Or let's just talk about 5 minutes. And it's an airline seat. You can't leave that open for 5 minutes. Or, if you do, what ends up happening is you have these makeshift business rules you put in. Oh, it's reserved for 24 hours. So you lock the seat, pretended like you bought it, but you didn't buy it for 24 hours, and then at the end of 24 hours, the release comes off. Well, the status is going to change. There's a stored procedure in there or a trigger that changes it after 24 hours and says, okay, the person didn't pay for it, the person didn't buy it, okay, it's in limbo, okay, and now it's released. That's an artificial way of facilitating a long-term transaction. We don't have that. We don't even have any currency control either. When one person has locked it, it's locked for everybody. It's hard to have multiple people looking at it. It's hard to have multiple people with concurrency protocols. Not suited. They're not suited for relational database design. So we use third-party libraries, or we use Java transaction authorities or something to make this happen in the real world. So scheme changes are difficult. Yeah, once you create the database and the database is working and you give it to your web designer or your application developer, Are they going to add columns to this to make the application work? Not such a good idea. Very hard to do those scheme changes. And then you're putting something in there, you're going to take it out of a third and you're going to put it into a second normal form or something so it works better with the application, which is actually a good justification if you're taking something out of a higher and putting it into a normal form, because you're working around transaction issues and things. So you're making it, let's put another key in there, or let's put another piece of information in there to make it work, which is a workaround. Relational database management schemes are also poor at navigational access. Yes, very hard to navigate. How are you going to see something in there and you have to do a query? So how are you going to go to a particular record? You can't. You don't know the record number. You don't know the record order. Do you know that with the object? Well, you can build a method to find the order. You can build a method to find the information out of the object. So with the objects here, you can have a history on the object. You can create a longer-lived transaction concept working with objects using Java and other object-oriented languages. So let's talk about object-oriented languages. What do we have here? Object-oriented concepts. Well, everything you know about object orientation from a programming perspective applies towards databases. So it's the same concepts. So abstraction, encapsulation, information hiding, objects, attributes, object identity, models, messages, and objects were made on top of entity relationship. So the modeling started out with entity relationship. Then we have object orientation, which is an extension of entity relationship. So wouldn't it be naturally, the next generation database should be object-oriented databases that are built on top of relational databases. Relational databases pattern imperative languages that work with sequences and flow control. And the program starts at the top and goes to the end, and we have variable assignments, and we have all these features of that type of language environment that's supported really well with entity relationship diagramming. So you'd naturally think that an object-oriented programming language should complement or work well with an object-oriented database design, and it does, which is why people like it and why there's definitely a growing trend towards object orientation. The number one biggest used database model these days, however, is still relational. We haven't made the switch yet. But object orientation does provide a lot of benefits. Polymorphic dynamic binding, a bunch of stuff. So let's talk about abstraction for a second. Well, in object orientation, it's the object is the entity. So we can come up with class models, object-oriented UML class models, that are very similar to entity relationship models. The only problem is we have to show 5 or 6 different models to show what one entity relationship model is actually doing. Because 5 different UML models are all going to focus on 5 different things. One of them is going to show the hierarchy of the classes. The other one's going to show the sequence of the class interaction. Another one's going to show the objects, not the classes. And you have all these different variations not well suited for entity relationship diagramming. So people still do entity relationship diagramming for object-oriented databases, which is kind of funny. So in terms of the abstraction, the idea is to identify the essential aspects of the entities and ignoring unimportant properties. So that's the abstraction of it. And then concentrate on what an object is and what it does before deciding on how to implement it. So that's a good focus. In terms of encapsulation, taking everything and putting it all inside of one object and calling it by something. It's the employee, it's the staff. That's encapsulation. So the object contains both the data and the structure and the set of operations used on it to manipulate it. Well, it's the abstraction of a data type if you think about it. An integer is an integer. We don't worry about the range of values that are inside of an integer or what we can do with an integer. We just make an integer. Information hiding is another component of object orientation that's built into the object-oriented database model. So separate external aspects of the object from the internal. So we separate the external from the internal. We hide the details. So if we have an employee object, we might not know all of the different fields inside of it, but we know that it has data that's associated. Well, an employee would have a first name, a last name, a hire date. And we keep all this stuff inside, and we make a new employee getting all that stuff for us automatically. So it allows the internal details of the object to be changed without affecting its application outside. So we have a get and a set method for each one of the data members. And we have the ability to fire the object and to hire that object and to do all sorts of different behaviors to an employee object. We don't have to worry about how to actually fire somebody. We just tell the object to do it, and it knows how to do it. So it provides data independence. And then the concept of the object, which is key to object orientation. So it's a uniquely identifiable entity, contains both attributes and a description of the states and the real-world behaviors. So really it's identity, state, and behaviors that are lumped together in terms of the concept. Well, entities have identity and they have states, but they don't have behaviors. Objects have behaviors, which are the methods. So when we think about writing the differences between an entity relationship diagram and an object diagram, if we add those three components on the object side, and we take away the behaviors on the entity side, we're just primarily concerned with those attributes. Those attributes are the states. What is the student ID? What is the student enrollment date? What classes did they enroll in? Stuff like that. Then we don't think about the behaviors like add a class, drop a class, order a transcript. So if we take all those behaviors, put them into the model, then we have a more powerful database. Because now we have a database where a student transcript as a concept can be created by running a method on the object request transcript. So when a student requests a transcript, the database could do the connections over all of the activity and get all of the information without running a query. It can actually have a procedure that runs that puts it all together. And then you can take the methods of the behaviors and link them to GUI components. And then if you do that, you have the database doing more work. So the reason why this lecture actually follows the previous one I gave you this morning was because one of them this morning was how can we make it more efficient? How can we make the queries run faster? And thinking about the design of the application and how do you make that application work with that database. And the database is the bottleneck. It's always the bottleneck. So how do you make it run faster? Well, if you make an object-oriented database and you build the behaviors into the model, and the model objects, each one of the objects has the built-in behaviors, you're just running the methods for the behaviors from the application. Not only do you have a closer integration with the application and the database, but you have a faster running database. Because you have the logic built into those methods, you're not running queries for this. So it's like almost, taking the advantages, all the advantages of object-oriented programming, stick them in a database model, run methods instead of queries on the database objects, and then use the queries when needed to do other functionality that you have. Because you can still run queries, but the queries are run differently. So you're not going to base it off of SQL, you're going to base it off of object orientation and more programming language techniques. But you're going to have a faster running system than you would if you had to take and create this behavior of the concept of ordering a transcript. Well, first of all, you probably, unless you have extra tables, where you're going to add stuff to, you're going to create a transcript for each one of the students after they graduate maybe. And then every time the transcript changes, you're going to have to update it somehow. But long story short, you have to pre-compile and preset all this data, put it into a table, and then query the table every time a student orders a transcript. Kind of time consuming, kind of slow. That's why it used to take 3 weeks for a transcript to show up. Now you can, I believe you can get them the same day now, actually. You can download them. But normally, the concept of ordering a transcript is really the process. In fact, even at ITU, when you download it, you're not getting the official, you're getting an unofficial. It's not being ordered. It's not being ordered because it's not coming out of the archive database, it's coming out of the real-time one, which may not necessarily be synced correctly. It may not even be accurate. It ain't even going to hold historical data, nor is it official. It could have been altered by you. So to get the official, it's two-part. One is because it needs to come from a university mail system. Like, has to be sealed and protected so that you know that the customer didn't change, or the student didn't change it. So it's stamped, approved, sealed. But it's also queried from the real data. It's not coming from the cache data. It's not coming from what we think is in the table of the current database of the students, it's actually coming from the official records, which is a different form. So we take a bunch of queries and we run them all together. We have a report engine that takes the results of all that, puts it all together for us, and puts it out on a page. A lot more work than creating a method and an object to give you the same thing. So, long story short, the method could be more streamlined, and it is through object orientation. So the definition of an object is very similar to an entity. So the definition is very similar to the definition of an entity. However, objects encapsulate both the state, the behavior. An entity only models states, no behaviors. So you can use that as part of your data if you wanted to on that paper you're writing. Entities don't consider behaviors, they only consider states. They have identities. There's an identity to an object, there's also an identity to an entity. In terms of the attributes, those are the states. So attributes are containing the current state of an object. So an attribute can be classified as a simple or a complex one in a relational database. And then simple attributes, and also in an object-oriented database, there's a very much a similarity with the attributes. And then simple attributes can be primitive types, such as integers and states and strings and stuff like that. They can also be literal values. And then complex attributes can contain collections or references. So if we look at the complex, as simple as a simple attribute is a simple attribute. That's all we have in relational models, a bunch of attributes. So if you think about that concept, it's really easy to translate that. You just take that concept, put it into an object, it's already there. But in a relational model, can you have a structure or an object that's inside of used as an attribute? No, you can't. There's no nesting of objects inside of objects. So inside the student table, you can't put a transcript. But you could put a transcript in an archived student table. If you're using a database, object-oriented database model, you can create a transcript object that keeps track of all of the student records and all of the student information, and then you just make an instance when you print that transcript of that object that's already compiled for you. Why do we have to generate a live transcript for all students all the time? After you've graduated and you haven't come back to the school and you haven't taken any more classes, we can archive a transcript object. And then it's much easier to print that out. So we don't have to run a query. We already have it. It's already stored for us. Can't really do that with a relational model. It doesn't work. You can save an image of the transcript, and you can save a picture, a PDF or something of it, and you can store that somewhere manually. But you can't have the database do it. So the database works with more complex data. Object-oriented databases work with more complex data and more multiple attributes that are associated, and then the whole object concept is supported inside of the database as well as an attribute. Reference attributes represent relationships, and then an object that contains one or more complex attributes is called a complex object. Well, we just don't have, we have one type of entity, an entity. We don't have complex entities in a relational model. So we also have object identity. Man, isn't that the name of the table that we created in terms of an entity? So object identifier is assigned to an object when it is created. So we can actually have a system generated identifier unique to that object. It can be an invariant, could be independent of the values or the attributes of its states and behaviors. And it could be visible to a user ideally. Or it could be hidden. So object identity, in terms of its implementation in a relational database management, the object identity is the value base. It's the primary key that's used to provide uniqueness. So if I said a staff member, we have staff ID, student ID, that's the object identity. In an object-oriented, we don't have to use something that's statically set. We can actually create instances of objects and actually use the ID of that object. As an example, student with a student ID 123 is statically identified as 123 in a relational model. But it could be student 123 who's taking this class. which could be identified as ID A. And then that class over there, student 1, 2, 3, is taking ID B and C and D. We can actually keep track of instances instead of just students. Because you could be a student and you could be enrolled in multiple courses. And you can have different object IDs for each instance of your object that you're using in each one of those courses, which is actually kind of a variation of the ID concept. So in a relational model, it's value-based. Primary key is used to provide the uniqueness. Primary keys do not provide types of object identity required for object-oriented systems. We don't have instance types, we have static types. It's almost like the difference between a static and an instance ID, and if you think about it. So keys are only unique within the relation, not across the entire system either. So if we had a global ID for an object, and each object was uniquely identified while the instances were made, we could only have student A, who's 1, 2, 3, who's that particular instance of that student taking a class, and we couldn't have another student with the same ID somewhere else. In a relational model, we can. We just create another table. So we can have graduate student table and undergraduate student table in a relational model, and we can have two students with the same ID, 1, 2, 3. And in that particular case, we end up with multiple identities if we try to use it globally together. So we couldn't take all the grads and all the undergrads and all this major and that major and that major, and if we had it all separated out that way, we could possibly have the same primary key used all over the place to identify multiple different students. And what about different years of students, or different terms and stuff like that? Leads to mistakes. In an object-oriented environment, we can keep more of a global ID system going. We can actually manage the objects by their IDs a lot more efficiently. So throughout the entire system. And the key generally is chosen from attributes of the relation, making it dependent on the object's state. What if you're no longer a student? Do we still have a student ID? I guarantee it, none of you guys are going to use your student ID when you leave this campus. Unless you particularly like your student ID for some reason, you're not going to use it ever again. Why would you use it? It's independent of you as an object. If it were dependent on you as an object, we'd know the ID. Because here's what happens with transcripts, which is actually kind of interesting. Student leaves and comes back and says, oh, hey, I graduated from your school 10 years ago, and I'd like to order a transcript. The first thing that the database would love to have would be your student ID, but you're not going to know it. I don't think anyone in this room is going to remember their student ID after they graduate 10 years later. I don't remember any of my student IDs from any one of the databases I was in, but that was my primary key. So now instead we have to make this database, take it out of third normal form, put it into second normal form, and use my social security number as well. So on the assumption that you understand what normalization is, that's a very good reason why we take something out of third and put it into second. If it's in second normal form, there's multiple ways of looking up the data. We introduced a bad design to it to make it a good design, because the business rules later on are going to say that if a student wants to order a transcript, and the only way we can keep track of the student is through their student ID, which is actually kind of a funny scenario. Because how does ITU do it? You don't have social security numbers. You have passport numbers. What if you don't remember your student ID? Maybe your name. You know how many people have the same name? I guarantee it, we have situations where we have interesting name combinations that are very similar. No first name or no last name. There's like a term for that they put in the database. And then you've got other names. It happens with America too. I mean, it happens in American universities as well. John Smith, There's so many different Smiths and Johnsons and Joes and Bills and Toms, and everybody's the same. And there's no social security number in there? That's why they started storing social security numbers to begin with. But long story short, it'll be interesting. In fact, I should find out what ITU uses. Because I know my U.S. passport number is not the same format as your international passport number. It's different. The numbers are all different. So I guess you'd have to keep the country of origin maybe, and then the number, perhaps. if they're holding on to that. Did they hold on to your passport number? No, Cevis has it, so they should. I know they have that information somewhere. So I would almost guess to say that's probably how they're getting a hold of you. Otherwise, you'll find out in 10 years when you want to order a transcript from IT. They'll go, I don't remember my student ID. Unless you just write it down and keep it forever, because later on you might need to use it. With the assumption they haven't recycled those student IDs. Because I know the student IDs have changed in format from when we moved to this campus. They changed completely. So, good question. I don't know. But that's because of this problem here. So if we had an object-oriented database, we could just use an object identity for you, and then that object identity would be something that was associated with you as an object. So it could be a combination of your passport number with something else. It could be formulated, or maybe it was auto-generated, who knows. But anyway. In terms of the implementation, which is actually what I'm talking about, programming languages use variable names, pointers, virtual memory addresses for the object identity. So, or C++, you can use an object ID to a physical memory address in the implementation of the database, some space, to keep track of those objects while they're running. Not necessarily for users of the system to keep track of the objects, but for the objects themselves inside of the application to keep track of them. Object is deleted, hopefully the memory is reused, and it may cause some problems if the memory is reused and you go back to an object and the object's changed or something. It's kind of like reusing a primary key for something else. And the data is not going to be valid. So the advantages of using a global object ID is obviously efficiency. It's fast. And they cannot be modified by users because they're not created by users, they're created by the object. So the user can't modify. And then they're independent of the content. So your object ID, it's like your social security number in the United States. It just stays around. Actually, you guys have social security numbers, don't you? So maybe that's what they're using. You're issued a social, don't ever lose your social security number. It's only good in the United States anyway. So that's probably what they're doing. Everyone's required to have a social security number?
I didn't give my social security.
I'm sorry?
I didn't give my security number.
You didn't give IT your social security number?
They don't have any requirements.
How do they keep track of you? Now I'm kind of curious.
He comes and goes.
He just comes and goes. They don't keep track of you. I'm sure they must be keeping track of you. Passport number?
Maybe.
But I know your number is a different number than I have. In format completely. And the passport numbers change by country, changes by when you got your passport, changes by a bunch of stuff. It's used for a different purpose. It's not used as a global tracking system.
They track with service number.
Cevis number. Cevis gives. Are you going to remember that number? How are you going to order transcripts 10 years down the road? Actually, someone asked the student services that. I'm kind of curious. Maybe I'll ask the student services. How does a student order a transcript 10 years from now? You got to have something. You can't use your student ID. And if you can't remember your student ID, does that mean you never went to the school? Anyway, now I'm kind of... All right, well, this is a good stopping point. Something to think about over lunch. Ask, how do you order I don't know. Maybe I'm going to ask... What if you don't remember your user account? How many email addresses do you think you're going to have throughout your entire life?
You have that.
Huh?
Once you forget the password, you have that. Forget the password. So
But isn't your user account now an email address, or it used to be an email address?
You used to give your personal email address.
Yeah,
So once you register with that, it automatically shows your user ID.
Yeah.
You
But you have to remember your user. You have to remember that name.
But you can, if you don't remember, can't remember username, then it will ask for
A password. If you, what if you remember? Oh, you could remember the password, but not the username, and get the username back.
They don't ask for password. All they ask is email address.
What if you don't remember? You know how many times I've done that with applications? You sign up for something, and then you go back, and what email address did I give them? And then I realized I didn't give him any. I gave him a bogus email address.
Security questions.
Security questions, maybe. Maybe it's the security questions or link. I'm going to find out, actually, because I'm kind of curious. What do they order transcripts with? Maybe passport number. Not all of you have social security numbers. Yeah. Alright, on that note, now that we've confused everybody about their status of their transcript 10 years from now, hopefully you'll be able to get one. In the meantime, let's take lunch. So I'm going to stop this lecture.
I just ordered right now.
You're going to order it right now? You just ordered a social security number right now?
No, no.
Or transcript?